I mentioned when we started doing precipitation reactions that we would soon be doing limiting reagent problems using precipitation reactions too. And what this is really leading us to is a conversation of doing limiting reagent problems using molarities. Now, the two examples that I'm going to go through in this video will both be precipitation reactions, but in reality, anytime we have molarity, we can do limiting reagent problems. So as we continue on into other types of reactions, you will see limiting reagent problems with molarity in those kinds of reactions too. I'll probably make additional videos of those just to give you additional practice in case you need it. But if you feel confident handling limiting reagent problems using molarity after this video, then there's no particular reason that you would have to watch any of those videos as long as you feel confident with the concepts. So let's review for a second and think about what are the big ideas when we do limiting reagent problems. So when we have these limiting reagent problems, we usually have reactant 1 plus reactant 2 making product 1 plus product 2. And whenever we have a limiting reagent problem, then we are told the information about both of the reactants. And that's how we know for sure that we have a limiting reagent problem. So we are given information about the quantities of 2 or more reactants in the balanced equation. So when we do limiting reagent problems, these are stoichiometry problems, and I'm going to draw this little diagram that you're probably getting a little tired of by now. And now we have more than one track. All right, so in this track, whenever we're doing our limiting reagent problems, we're going to follow our track and our process the same way. So our process, just to review, is that we're always identifying A and B, and then we're identifying the start and the end. And then we're following whatever trail it is that we need to do to get between our starting point and our ending point. And so this is any stoichiometry problem. And for a limiting reagent problem, we just have to do this twice, because we will have 2 starting places, A. And in these particular examples that I'm going to look at right here, we know that we're going to start with this information. This is going to be our starting place for all of the problems that we do in this video, and this is going to be our ending place. So we're going to use the molarity and the volume to get ourselves to moles. We'll use the balanced equation to get from the moles of our reactant to the moles of our product, and then we're going to use the molecular weight to get to the grams of our product. So let's see a couple of examples and practice doing these skills. So let's try a scenario like this. We are told that you mix 45 milliliters of 0.6891 molar nickel nitrate with 65 milliliters of 0.7122 molar potassium carbonate. And the question is, what is the theoretical yield of nickel carbonate? The other way we could write this to make it even more, I don't know, interesting, challenging, to hit more skills would be to say, what is the theoretical yield of the precipitate? And the reason why this would be more interesting or more challenging is that you also have to write the balanced equation. So let's go ahead and start with that. We can see what our two reactants are. So this is one of our A values, and this is another A value. So we can see our reactants, nickel nitrate. And since we're told that it has a concentration, this implies that it is aqueous. And the same thing is true for our other reactant, K2CO3. And of course, we also know that they are soluble because nitrates are always soluble and potassium compounds are always soluble in water. So we just got told that we would have nickel carbonate, but if you didn't know that, how would we figure that out? Let's take a look.
We're back.
The first thing we always want to do is figure out what the charges are on our compounds, or sorry, we should figure out what the charges are on our ions, our individual ion parts. So if we look at this, we know that nitrate is, and I just noticed a typo. I actually intended this to be nickel nitrate 3. Okay, so let's fix that. Okay, good deal. So we've got we've got nitrate, which is a -1 charge, and we have 3 of them, which means that this is a nickel 3+. And then over here, we know that potassium is a +1 ion, and carbonate is 2-. And so when we react these to make nickel carbonate, because carbonates are usually insoluble, then we can see that the 3+ and the 2- our least common multiple is going to be 6. So that means 2 of these 3+ charges will give us a total charge of +6, and 3 of these -2 charges will give us a total charge of -6, and so this is now a neutral compound. And then what's left over? We have potassium and nitrate, and we know they form a soluble compound. So now we need to balance it. So let's take a look. If I look at the nickels, I can see I have 2 nickels over here. I better put a 2 out front. If I look at the carbonates, I can see I have a 3 out front. And so when I look at everything else, it looks like I'm going to have 6 potassium nitrates, and that will balance it. So when we are starting our tracks, you can choose from either starting place. It does not matter because we're going to do it twice. So let's go ahead and start on the A1 track, which it's only A1 because I listed it first. So we need to review our process. If you need to go back up here and take a look at it, that's totally fine. So we're starting with our volume. We're going to use the molarity to get us to moles. So let's go down here and do that. So our volume is 45 milliliters. And we're going to convert that into liters because our molarity is in moles per liter. So our molarity is 0.6891 moles of nickel nitrate per 1 liter of solution. And our stoichiometry tells us that 2 moles of nickel nitrate are combined to make 1 mole of Ni2CO3 nickel carbonate. And now we need to calculate the molecular weight because we're heading toward grams. And actually, I didn't even say that. I just said theoretical yield. So in a problem where I ask for theoretical yield, you could just calculate the moles. But let's do it in grams just for the practice. So when I calculate the molecular weight here, I have 261.512 grams of nickel carbonate per 1 mole of nickel carbonate. And so when I do all that calculation, let's see, my milliliters cancel out, my liters cancel out, my moles of nickel nitrate cancel out, my moles of nickel carbonate cancel out, and I am left with grams of nickel carbonate, which is what I want. And when I did this calculation, I get 4.055 grams of nickel carbonate. Now, I've done this once, but this is a limiting reagent problem, so we have to do it again. So I want you to pause the video and calculate from the 65 milliliters of 0.7122 molar potassium carbonate and see what kind of a product you get. So I'm not going to write out all the setup because it's exactly the same with the different quantities here. But when you started from 65 milliliters of 0.7122 molar potassium carbonate, then you should have gotten 4.035 grams of nickel carbonate as your answer. So which is our correct answer here for the problem? What is the theoretical yield in grams? Well, when we do limiting reagent problems, we know that we need to go with the smaller of the two numbers. It means that the potassium carbonate is the limiting reagent, and we will run out of it first. And so when we run out of potassium carbonate, we've only made 4.035 grams of nickel 2 carbonate. It's actually not very much different from the other one, but that's how limiting reagent problems work. Whatever the smaller number is, that is our answer. Okay, let's try our second example. In our second example, we have 18 milliliters of 1.225 molar sodium phosphate that react with 45 milliliters of 1.512 molar silver nitrate. And our question is, how many grams of precipitate will form? So let's take a look and review what we need to do. So our first step is to predict products. And balance the equation. Our next is to identify our A1 and A2 and our B, and then identify our start and our end points. And then we need to solve it. So pause the video and try all these things. All right, welcome back. Hopefully you were able to see that sodium phosphate is soluble because sodium ions always soluble, and that silver nitrate is also soluble because of nitrate, and that our ion charges are going to be such that we're going to make silver phosphate with 3 silvers, and that's going to be insoluble, and then left over we have sodium nitrate, which is soluble. And because of our stoichiometry, we need 3 equivalents of our silver nitrate and 3 equivalents of our sodium nitrate. So that's step 1. And in our step 2, we can identify that our A1, well, it doesn't really matter which order you do them in, and A2 are our 2 reactants, and our insoluble product is B. So when we look at our starting place is going to be the volume and the molarity of A, and we're going to end with grams of B. So from our A1 track, you should have found that we can produce 8.877 grams of silver phosphate, starting from our sodium phosphate. And from our A2 track, you should have calculated that we can make 9.131 grams of silver phosphate. And so, of course, our answer is this smaller quantity right here. If you need any help with these calculations, please make sure to talk to me right away. I'd be happy to go through calculations and give you more examples.